DU 2024, question number 4A, advanced MME. For a function y equals to fx with the domain defined as the closed interval 0a, where a is a positive constant, find the area under the curve using Riemann integral. Give an approximated expression for this area. Okay, so let us see how we are going to approach this problem. This is basically the entire concept of Riemann integral. So let's see how we can approach this. Okay. So basically what is given to us is this. We have a function y equals to fx, and we have this interval 0 to a, and we have to find out the area under this curve. Now, Riemann integral was given by a mathematician who was named as Riemann, very famous. Now, he gave us two ways to look at the area, okay? Because the basic unit of areas are the rectangles. Now, let us observe carefully. What we can do is that we can divide this into sub-intervals. Okay, when I say sub-intervals, what I mean to say is that I am dividing this whole interval 0 to a into intervals. Okay, this is the first interval, this is the second interval, this is the third interval, this is the fourth interval, this is the fifth, and so on. So what is going to happen is that he gave us two ways. He said, okay, now first we can do what we can do. We can actually calculate the area of the lower rectangles. Okay, the red ones are the lower ones. So something like this. And then he said, add these areas to find the approximate area under the curve. So basically, of course, this area is not the exact area under the curve, but it is approximately equal to this area under the curve. Notice one thing, as the partition will become finer, this area of these lower rectangles will become more and more close to the area under the curve. Okay. Now, similarly, he said we can also do it like this. Calculate the area of upper rectangles. Something like this. Okay. So what we can do, we can actually approximate this area either from the lower rectangle or from the upper rectangle. So when I am approximating the area under this curve using the lower rectangle, the area is less than the actual area under the curve. And when I'm approximating this area using the upper rectangle, the area calculated by the upper rectangles is more than the actual area under the curve. Now we can notice one thing, that as we increase the number of elements in this partition, the lower sum. What is lower sum? The lower sum is sum of areas of all lower rectangles. Okay. And similarly, we will have upper sum. Upper sum is sum of areas of upper rectangles. Okay, so what is happening? As we increase the elements in the partition, the lower sum will increase and the upper sum will decrease. So basically what is happening, as we are breaking our interval 0 to a into smaller and smaller subintervals, the lower sum and the upper sum will tend to converge to a common area. If that happens, okay, if the lower sum, all the lower sums are converging to I, and all the upper sums are converging to I. If both these limits are same, this is something known as sandwich theorem. Two functions are sandwiching another function. If these two functions are approaching a limit, the middle function will also approach the same limit. Same thing is going to happen over here. If the lower sums are converging to I and the upper sums are also converging to the same I, this I is nothing but the area under the curve in the interval 0a. Okay, so basically, why do I say lower sums are converging to I? Because I do not have one lower sum. With respect to each partition, I will have a sum. Okay, so now let us formally define what is a partition. Okay, so if you have an interval like this, okay, so we define a partition Pn, okay, as this 0, x1, x2, x3 till xn. Okay, this xn is nothing but a, and this 0 is should be named as x0. So what is happening? This is my interval 0 to a. So I have x1 here, I have x2 here, I have x3 here, I have x4 here, and this is my xn, and this is my xn minus 1. So I am partitioning this interval. Now what is happening? I get subintervals 0 to x1, x1 to x2, x2 to x3, and xn minus 1 to xn. So how many subintervals are there? 1, 2 till n. That means I have n subintervals, but how many points are there? N plus 1. So any partition containing n plus 1 points has n subintervals. Okay, so now what is happening in these subintervals? If I look at the upper sum, if I look at the upper sum, okay, with respect to a partition Pn. So this is my partition Pn. As n varies, the number of elements varies. So if I look at the upper sum of this function with respect to this partition, this is nothing but xi minus xi minus 1. Now what is? Every partition has a width. इसका width x1 है, x1 minus 0. The width of this is x2 minus x1. The width of this is x3 minus x2, and so on. So we are already seeing that the partition Pn has n plus 1 points. This is the first subinterval. This is the nth subinterval. This is the ith subinterval. If we look at the length of the ith subinterval, if I write it as delta xi, this is nothing but xi minus 1. And if I multiply this with the maximum value of f over the ith subinterval. So what is f of mi? This is the maximum value of f over ith subinterval. Okay. Again, let us look at the graph. Suppose I had a function like this. This is 0. This is a. And suppose we are partitioning. So let us look at this partition. Okay. So if you look at this particular subinterval, the upper rectangle, this is the width, which is, suppose this is the ith subinterval, this is the width, and multiply with the maximum value of f. So this is the maximum value of f. So this is the height. Okay, so I will get the area of the upper rectangle. Okay, and this is the area of the ith upper rectangle. So this way we are going to start with I equals to 1. Okay, and we will go till n because this is x naught. Okay, so summation I going from 1 to n, f of mi xi minus 1. This is the upper sum with respect to the partition Pn. And let us denote this by capital Mi because it is representing maximum. Similarly, if we look at the lower sum of this partition is going to be summation I going from 1 to n, f of small mi xi minus 1. Where what is f of small mi? It is the minimum value of f over ith subinterval. What does it mean? So if you look at this subinterval, okay, and if you look at the minimum value, this is the minimum value. So if you take this as the height, So this is your f of mi, and multiply it with the width, so you will get the lower rectangles. So if you add all the lower rectangles, you will get the lower sum. So what we were discussing with respect to Riemann integration, now these partitions will keep on getting refined and refined. What do you mean by that? N will become larger and larger. We will try to increase the number of subpoints in these partitions. So when the subpoints will increase, the lower sum will increase and the upper sum will decrease. So if limit n tending to infinity, u, p and f is equal to limit n tending to infinity L, P, and F, okay, is equal to I. We say F is a Riemann integrable over the closed interval 0a. This is the definition of Riemann integral. We have to look at the sequence of the lower sums. We have to look at the sequence of the upper sums, and they have to converge to a common value that is known as the integral. So this I is nothing but integration of 0 to a fx dx. And this is also known as the area of this function under this interval 0 to a. If my function is, of course, over above the x-axis, there are different methods. When the curve is below the x-axis, then we have to partition the function into subintervals. Like, for example, if we have a function like this, so we will first talk about this function, then we'll talk about this part. We calculate this integral, we calculate this integral, we multiply this with the negative sign because this is below x-axis, and then we add these two and we find the area. But technically, what is a Riemann integral? You have a function, you have a interval, you take the partition, then you refine the partitions, you take the upper sums, you take the lower sums, you take the sequence of lower sums, you take the sequence of upper sums. If both the sequences are converging to the same value, that common value is called the value of the integral of the function over the closed interval 0a. And if they are not converging to the same value, the function is not integrable. So that is the definition of Riemann integral. And that is how we calculate the area of a function under, a curve within two particular values, for example, 0 to a here, using Riemann integral.